And there you go.
Okay, well, I guess we're going to start up. I welcome all of you to this year's tutorial 2020. I'm Michael Way, or you can call me Mike. I'm joined here by Kostas Sigouridis, who you can see drinking out of a coffee mug at the moment. Why don't you say hi, Kostas, so that your
Hi
screen
guys,
pops up.
and thanks for showing up.
And Igor Alienov. Igor, can you say hi?
Okay.
He's got the cosmic background, far out background, and I have the easily spotted unicorn background because my man cave is in my daughter's room, as it should be. So I think we're just going to go ahead and get started, and hopefully as others dial in, they'll pick up, because the beginning of the tutorial is quite soft, I would say. We're just going to cover what the capabilities of the model are. But I would just say first is, here's a list of people who helped put this tutorial together this year. And you can see a link to last year's tutorial put on YouTube and the one the year before that. I should add that many people have used these YouTube tutorial links to actually get the model running. And if we go through something a little fast, don't worry, we're going to put this year's tutorial up online as well. So don't fret if you think you've missed something that you thought was really important. You'll be able to go back and review it without any issue. I think you all know how this works because you're here, so I'm not going to go through that. Here's our schedule today, or what our tentative schedule is. Hopefully we'll keep to it at some degree. These are all Eastern US time zone times. As I said, we'll do our best to keep to it, and hopefully there'll be enough breaks and such to keep your interest going strong. And this is the schedule for tomorrow, where we have a lot more guest speakers or members of the group talking about different aspects of the model, which I hope will make it a little bit more interesting in a sense. Okay, so I would assume you all know what a 3D GCM is. This is a picture of, a kind of idealized picture of what a GCM is. People often ask us, as you'll see later on, why our configuration files for the GCM are so complex. It's because GCMs are complex. There's a lot of options in a GCM, and I would say that we see papers in the literature every month that are using GCMs in ways that we find either inappropriate or really stretching the bounds of what the physics in the GCM can do, or making assumptions that they don't understand well. And that's one of the reasons we hold this tutorial, to give you some idea of what the model is capable of, and maybe more importantly, what the model's not capable of, in a sense. But you can see here there are some limitations. If we say time scale simulated so far, we say roughly 10 to the 4th years. Those would be Earth years. You can see the vertical range of our model. Its model top is around 65 kilometers. We can't really simulate escape, and we only get mixing ratios up into the stratosphere, and we are limited to the shallow atmosphere approximation, which means we cannot do mini Neptune or larger type worlds. This is a terrestrial GCM. This is one of these idealized pictures again of what a GCM looks like. There's a coupler, and then there's all these different components, all of which this GCM includes: sea ice, land ice, the ocean itself, the land part of the model, and of course the atmosphere and the chemistry. And we will try to touch on each of these at some level throughout the tutorial to give you an idea of what the model is made out of and how each of those things work at some level anyway, at least at a beginner level. So one of the things I like to do is point out some of the papers that we've used, the model has have been written using the model, excuse me. And this, of course, is the key paper that is the model description paper. Unfortunately, not every planetary model has a descriptive paper like this, but I think it's one of our prouder achievements that we actually managed to write such a paper to describe the model, at least in some detail. And it'll make your life easier too. If you use this model, you won't have to explain everything, as many people often do when they're using someone else's model. You can often refer to this paper when you use the model to explain what the different components of the model are actually doing. So I thought I would go through a few papers and show you a few extensions of the model that are a few of the things the model has been used for. This is some pictures of Archean Earth. Basically, is modeling Earth through time from 2.9 gigayears ago to the present day. This is a paper from in a book chapter of Tony Del Genio et al. We've also done ancient Venus simulations. Ram has posted a link to a more recent paper in the chat window, an extension of this work. Basically, what we're doing here is exploring the inner edge of the habitable zone, which is a very popular topic, as many of you know, to try to understand if our inner edge studies tell us something about Venus and whether Venus can tell us something about inner edge studies. Here we have an example from our model description paper done by Igor Alienov, showing how the model works with modern Mars, but unfortunately without CO2 clouds. That's an item to be developed in the near term, showing how the surface pressure is varying as a function of time and follows not too badly the Viking 2 data, which was on a fairly large plane, and this particular version of the model is running a fairly low resolution version. And Igor and Kostas maybe we'll talk a little bit more about Mars versions of the model a bit later in the tutorial. Hypothetical Venus-like worlds near M dwarfs in this case, so not around G dwarfs like our sun. You can see this is a paper that was led by Stephen Kang using some simulations I had done, which I thought I would never use. And Stephen and I have found a way to make some use of them at some level. This is one of our more popular works. This is the Proxima Centauri B system that was led by Tony Del Genio, where we did a lot of 1-bar type atmosphere, aquaplanet simulations, all the way up to 10-bar N2 CO2 dominated atmospheres. In this case, CO2 dominated 10-bar atmospheres, as you can see in the table that we include from the paper, table 4. Ancient lunar atmosphere. This is a project that's been led by Igor Alienov, looking at very thin atmospheres, temporary or transient atmospheres, as we say, on the moon, very early in its history from volcanic outgassing. And then, of course, there are these large obliquity studies that have been led by Chris Kolos, again, very popular in the literature to do studies like these. All of these studies I've discussed so far and will continue to discuss all use our fully coupled ocean version of the model, which makes our model a little unique. A lot of the papers in the exoplanet literature are using what we term slab oceans, and we'll talk a little bit more about those slab or mixed layer oceans tomorrow. Then we have some inner edge parameter ensembles. This is following along the lines of Jun Yang's work from 2014, but Jun didn't use fully coupled ocean in those simulations, and these were fully coupled oceans and mixed layer slab, or what we call in-house Q-flux equals 0 oceans, which we'll talk a little bit more about later in the tutorial. And then you want to ask, why do I mention all these papers? And it's very important because the fastest, as I say here, most reliable means to get a new planet running is to look at our old papers and find a planet that's similar to one of the ones that we have already published. You might have one that's very different from one of the ones we've published, and that won't help you. But if you can find one that's similar, in general, we try to publish all the configuration files, or what we call the rundeck files, the boundary condition files. What I mean by that are like topography, river directions, some of the model output, and some of the plots and associated materials for all of the papers that we publish with this model in-house. And we would encourage you to do the same. And in fact, the journals are requiring it at some level. The last paper I published, the journal really wanted me to put it in a long-term archive. And in this last case, we put it on Zenodo. But if you click this link at the bottom of this page, it'll take you to an internal website hosted down at Goddard Space Flight Center, associated with the supercomputing center down there, called NCCS. That's why it has this portal.nccs.nasa.gov in its name. And there you can download a lot of the files that we'll talk about and which you hopefully will have a better understanding of as we go forward. Okay, so there are some caveats, as I mentioned at the very beginning, about what kinds of atmospheres, what kinds of stellar spectra we can run with this model, and we'll discuss them as time goes forward, hopefully in some detail. Now, of course, we should talk about what the model cannot be used for. One big limitation for a lot of GCMs, not just ours, is that we cannot have variable atmospheric mass for a mix of constituents, meaning that the mean molecular weight of the atmosphere cannot be changing by large amounts, say more than 10%. When would you see a case like that? When you have a lot of water vapor in the atmosphere, example. You can see changes like that. Or if you have a lot of carbon dioxide in the atmosphere and a lot of the carbon dioxide is condensing out, and over time, for example, the model will become not so accurate in those moments. We have problems with super Earths, as they are called, basically because the shallow atmosphere approximation begins to go non-valid. As I say, where the thin atmosphere goes valid. Super thick oceans. So there's a question mark there. We have been doing some in-house development on doing super thick oceans that also get around the shallow atmosphere approximation. And Tony Leboissetier will talk about that a little bit tomorrow, about the ocean development aspects of the model. Really cold planets. So we have some problems doing outer edge studies with oceans. The one thing our ocean does not like is being frozen all the way to the bottom. That's because our model has trouble changing surface types, in essence. In theory, it should change to an ice land type, and the model cannot do that. So it's something you have to be a little bit cautious of. The technique that we have typically used is to make the ocean deeper so that we can get to equilibrium, which we'll talk about later, radiative equilibrium, before the ocean freezes to the bottom. As I've already said, mini Neptunes and gas giant planets are really off the cards, off the table for us in the current version of the model. And remember the acronym, if you can, because most of the time we can't remember it. Resolving orbital and climate keys of Earth and extraterrestrial environments. Like many other GCMs, we do have a South Pole anomaly, which means that the South Pole point has to be, the one single grid point of the South Pole does have to be land. Often in aquaplanet scenarios, what we do, we set that to 0 topography, so it's at the same height of the ocean. We have not noticed any major effects. Some GCMs even have to have both poles. Of course, our goal is to get rid of this anomaly, and we have made some progress on that. Hopefully in the next version of the model, we'll be able to get rid of it. And there are limitations, as I've mentioned, in the radiation and chemistry aspects of the model, which again, we'll try to cover some of. Okay, so we have some documentation of the model. I wouldn't say we have great documentation. Like all GCMs, or at least most of them, these GCMs are written by scientists. They want to do science. They don't want to write documentation, and we're no exception to that. So that is some limitations. But if there's something you need, you can write us, and hopefully we can reply. But this gives you some ideas of documentation in the model. Okay, and then this is just a list of contacts and different people working on different aspects of the model for us. Should remember that our model is a subset of a much larger group, a much larger model, the Earth GCM model at GISS, that participates in the IPCC and CMIP studies. And so some of the people in our group do double duty in a sense. For example, our current cloud expert is Andy Ackerman. He really works on the Earth side of the house, but he is doing some work for us on the planetary side of the house. On the chemistry side, we have Kostas Sigaritas, who is going to be talking about that a little bit, and Sonny Harmon, who's now a civil servant out at NASA Ames, but he remains a core member of our group. Aerosols, again, Kostas can help with that. If you want to know about how to set up various planets, orbits, and things like that, you would write me. For radiation, our main radiation person is Eric Wolf at University of Colorado. He's also a core member of the team. If you have any questions about the old GISS radiation, which is highly tuned for Earth and completely inappropriate for anything other than modern day Earth, you could reach out to Andy Lasis. He wrote our original radiation scheme. The advantage of the GISS radiation is that it's extremely fast. It's at least 2 times faster than the Socrates radiation that we use. We'll talk a little bit more about that particular radiation package that we use later. Atmospheric composition, again, Kostas. Debugging issues, you would write all of us, but remember, we're scientists. First, debugging, you should do your best. We'll give you some tips on how to handle debugging of the model. Calendar or rotation issues, meaning different spin orbit couplings and things like that, would be Tom Clooney, and Tom will talk a bit about that tomorrow, about those implementations. Biology related things, if there are any. We don't have many biology in the model, at least not on the planetary side. That would be Nancy King, and for land surface, that would be Igor Lianov, who we'll talk a little bit later. As I mentioned before, for ocean and sea ice issues, that would be Tony Leboisier. And we have an in-house NetCDF viewer. This model produces NetCDF output. We have an excellent developer who's developed Panoply from the scratch named Robert Schmunk. So you have issues with Panoply bugs or other features you would write Robert and ask you for that. He's fairly responsive. And it's and we're fortunate to have Robert running that package for us. Okay, I'm going to let Kostas take over from here to talk about different aspects of the model. Hopefully.
Yes. I'm starting the presentation and also trying to unmute myself at the same time. So let me share my screen.
Stop my share.
And I am supposed to be sharing now this thing here. Okay, so hopefully you see my screen.
Yes, excellent.
Okay, perfect. So there are a number of names that have been used in the past for this model, and that has caused some confusion in the literature. So I'm listing a number of things here. We're trying to do our best now to keep that consistent. So the GIS model E2 is an old version of the model that was used for CMIP 5. And then the current workhorse version is the GIS E2.1, which is used for the CMIP 6 activities. And the results of it will also go into the IPCC report that is being drafted as we speak, actually is under review. Then in the ROCKE-3D world, which is essentially the model we're discussing right now, is the GIS model E2 with several improvements, the most important of which is Socrates, to be able to handle other planets. And the calendar, of course, is another big thing that we have. Then there are three different versions. One is the Planet 1.0 is the one that we'll be discussing today. Planet 2.0 is almost ready. There is one thing that is missing. It's a key thing that is missing, but it's only one. And this is why we're not presenting you the Planet 2.0. Everything you will hear here in these 2 days is going to be on the technical side mostly, so applicable for both model versions. And then we have a Planet 3 version that we will be working after Planet 2 is frozen, and after the Earth generation Model 3 is also frozen, which will include the major change that it includes is cloud microphysics. And so we do not have a date for when this is going to happen to be released for usage, but it's not going to be in the next month or two. So we're working on that. So the next model you will be receiving is Planet 2.0, and we hope that this will not be very long from now. Then we have three different ways to simulate atmospheric composition. One is called NINT, which is what we will be discussing mostly today and tomorrow, and this stands for non-interactive. So you prescribe the atmospheric composition based on some tricks that you will learn here, and this atmospheric composition does not change with either spatially or with time. And so you just simulate a time slice, a climatological time slice of a given planet. Then we also have OMA matrix, which are atmospheric composition prognostic packages. OMA stands for one moment aerosols, so we can simulate aerosol mass, and then we make assumptions about aerosol number for if you want to simulate size distribution. But if you really want to simulate size distribution, you should be going to matrix, which resolves both prognostically both number and mass concentrations of aerosols, and you can do proper simulations of the evolution of size distribution both in space and time. We're not going to discuss in detail about those things, but if you are interested in something like that, they have a significant CPU performance footprint, and so the model will be much slower. And but it is something that we're using all the time for the Earth model, and we're planning to be using for certain things here. So if you're interested in that, you need to be contacting me. Then terminology. You should have seen those things in your preparation for here. So there is the .model ERC file that you all have in our home directory, and you should be having that properly set up for your environment, or else things don't work. Then there is the main directory for that contains all the model code, essentially the whole Git repository, and it can be named any way you like. This is an example here that someone might have it in their home directory under model E2_planet_1.0, and but it can be really anything. And then inside that there is the templates directory, which contains the certain rundecs that contain that are vetted to create something meaningful. And so we will be discussing about those. You have already used it by the command make rundec that you had to do. So the make rundec command that you used takes a given template from the templates directory and then creates that, converts it into a usable rundec and puts it into the dex directory. Now, frequently, a template does not need any modification to be called a runtime rundec. But you should remember, and I cannot stress that enough, you should never copy a file from the templates directory into your dex directory. You should always be using the make rundec command if you want to do so, even if you think that the template rundec needs no modifications at all. And then the important thing is where all the work is being done is the source code, which is into the model directory and also some subdirectories. We will not be touching the model code too much in this tutorial, because there is, if you start with discussing about the code and things that you can do with it, there is no end. The model has some hundreds of thousands of lines of code. There is no way to even scratch the surface in a 2-day tutorial. So we will be skipping that, and we will be giving you the information that you need to know for running the model as it stands. And if you want to develop new components in the model, then you will have to probably consult us for how to start with, and then you will be ready to go. Important things that the model has is, of course, where the input files exist. And the input files can be anywhere. So there are some core input files that the model is using, and these exist in a directory that is defined under the GCM search path variable inside your .model ERC file. So you have done that already, and you can go and check what you have there. Then if for some reason you don't have a file in that directory or directory tree, then you need to point a file from somewhere else, then you need to provide a full path. So in the rundec, and we will go through that, in the rundec, if you say here's an input file, and the file name does not start with a slash, then the model will try to find it inside the GCM search path that you have defined. If it does start with a slash, then you have to provide the full path. Then the model, while you run the model, you need to make sure that that the input files are accessible to the model itself. So if you are running on a supercomputer, is the most common place that this might not be obvious, because the moment you run something on a computing node, that computing node might not have access to the full directory tree that you see when you are just doing your work in a login node. And for that, you need to make sure that you are putting your files in places where the compute nodes of your computer are able to access. And then the output files is the directory where the things are saved are defined into the save disk variable in your .model ERC. The model creates massive output. Depending on the configuration you might be using, it can, and the duration of your simulation, it can easily fill up your disk space. So you need to make sure that this save disk is in a place where enough data storage is available. And you can always go see the output by going into that directory and then follow the subdirectories. But also from the dex directory, there will be a link, a soft link created to the appropriate directory. So to explain that with an example, if in your dex directory you have created a run-deck with the make run-deck command that is called runid, so you will be having the run-deck in there called runid.uppercase-R, and then there will be a soft link that points to the subdirectory inside save disk with the same name, runid. And then from the dex directory, you can access everything you want. Then going into the run-deck, I think that in the instructions we have not told you to go and make any changes in the run-deck. The only thing you needed to do is to run the setup hour. So, but in case you have looked at it, it contains a lot of lines of information. And it is overwhelming, and there are very few people that really know every single line of it, and you don't have to know every single line of it unless you are planning to modify it. So the template run-decks you will be using, as I mentioned, are well tested, and you can trust them, and then you need to only understand the pieces of the run-deck that you are trying to alter. So the main things that the run-deck has is a very long list of the object modules, which is essentially the Fortran files that you are requesting to compile when compiling the model. And these are files that live in the module directory and some subdirectories of it. The components are also Fortran files that are more standalone entities. So they are in subdirectories inside the module directory, and they can be built standalone. So you don't have to define the individual files one by one. You only need to provide the subdirectory that you need to compile, and you need to make sure that in that subdirectory, a make file exists that explains what needs to happen. And it might sound complicated, but chances are that you don't have to ever worry about those things. These are meant to be there for big development projects, and if you want to do those things, then you are more than welcome to do so. But for the regular users, these are just things that you need to understand what they mean, and you don't have to worry about how to manipulate them. Component options is a small piece into the run-deck, a few lines, maybe 2 lines if I remember correct, that explain certain configurations of the components I just mentioned. Again, you don't have to worry about that. And then the important thing is the data input files section. This is where everything, the model will find all of the external input that it needs. So it can be emissions, it can be boundary conditions, it can be anything that the model is reading. Any file open and file read and file close thing that happens in the Fortran code should be defined in here. And you will be modifying this, and we will be discussing a lot about those files later today and tomorrow. Then there is a part in the run-deck that is called label and name list, which essentially says what is the run name, or we usually call it run ID. And this matches the name of the actual file name of the template. And you can also put some comment on the side that you will be seeing in all your output files. It's only 1 line. You will see it. It's very easy. And then there's the third really big part of the run-deck, which is the parameters section, which is encapsulated by a parameters and the end parameters lines. And in there, you define a lot of things that you want to say to the model, here is a value that you need to use instead of whatever default the code has. And that sounds easier than it is really, because you cannot go into the model, pick a variable and say, hey, here's a variable into this subroutine. I want to change it, and then you put it into the run deck and it changes. You need to have a certain way to make the run deck and the code interact so that this link will be established. And there are a few hundreds of examples in the code of things that can be defined like this. And if you want to modify, to create your own, chances are that there is a good example for you to replicate. The reason why we have this is because if you want to do, for example, sensitivity simulations, and you want to make, or you want to make an ensemble set of simulations, or in any way, if you want to make simulations that differ by very few things across your experiments, then the standard way is that you need to go into your code, you modify things, and then you run the model and you have several flavors of the code. This is ugly, and it can easily create confusion, and it can make things very complicated and even lead to mistakes. So, and not even to mention that every time you make one change, you need to recompile the model. The nice thing with having those runtime parameters is that you can define them in the run deck, and then without even compiling the model again, you can simply change those and run any set of experiments that you want. So if you have, let's say, a range of CO2 concentrations that you want to test, you can have 10 different run decks with one line being different, the run deck, the parameter that controls the CO2 concentration. And then with the exact same model code, you run your 10 experiments and you have a very clean set of run decks to compare when the time comes. And then the last part is the 3 lines at the very bottom of the run deck, which is called input Z, and it contains the start and end times of the model. And I will come back to what that means in general. So for the key template run decks that we will be discussing here, and we recommend for you to use, you can see those names here. And these are for the Planet 1. The Planet 2 has many more run deck options, but we're only going to be discussing about those. So the first one is, so P stands for planet, and then there is a number which is really something that is a historical significance, so you don't have to pay attention to it. Then uppercase S stands for Socrates radiation. M40 stands for medium resolution, which means 4 by 5 degrees and 40 layers. And then it can be 3 options. One is that there is no letter, and so the P4S M40, no lowercase letter between S and M, which means that the sea surface temperature is prescribed and the sea ice is prescribed. And then if it is a Q, then a Q flux, heat surface flux exists. And then based on present day Earth, unless you modify the file. And then the lowercase o means that the dynamic ocean is fully coupled with the atmosphere and the rest of the model. So these are the 3 different options. And then we also have a PS Mars. There is no ocean in that configuration. It's only a desert planet. So these are the 4 template run decks that we are recommending you to use. And remember, you never copy them to your decks directory. You create, you do a make run deck from your decks directory to create something. If you want to use anything else from the templates, please contact us before. There are several run decks in there that are extremely useful. And then there are equally several run decks that are obsolete and nobody took the energy to actually delete them, so you should not be using them. So if you have a new idea and you think that one of the template run decks is conveying that idea, please contact us before starting using it for production. So I guess everyone has a terminal window available. So if you want to go check those differences, you can do that. Should we do that now? Like 5 minutes, 3 minutes to leave people browse the differences between those three run decks and see how they look like?
Yeah, I think it's a good idea.
So you should go now into your templates directory and compare those different run decks that you see listed here. So again, the P1SOM40 is a fully dynamic ocean coupled with the atmosphere. The P4SQM40 has a Q-flux ocean, and you can compare it with a dynamic ocean to see how to do it. I mean, I usually use Vim diff. There are several other diffing options you can pick. I'm sure that everyone has their own favorite. And then you can even compare the P1SOM40 with the PS Mars, and you will see how vastly different those run decks are. There is also a link.
Why don't we? Yeah, I was gonna say, why don't we take a break? Because we're almost at our 15-minute break, so people can take a look at this while we do our break. Even so, go ahead, Kostas.
Okay, yeah. So there is a link down here that you can see all the different variables that you exist with some minor or not at all documentation. It's depending on how every variable has been defined. How about you go through those run decks. We will be monitoring the chat window if you want to ask any question about those. And we'll take the break right away. What's coming next? Yeah, okay. We'll take our 15-minute break, and then I will continue with a couple more things.
Yeah,
Okay.
Kostas, I was wondering, maybe it's better for people just to try to generate run decks rather than going to templates, because then they will be looking basically.
Yeah, I was thinking about that while I was speaking. So
yeah.
I said that the make run deck is what you need to be doing in your decks directory, and that's what Igor is proposing, and it's a good idea.
Yeah.
So why don't you go ahead and do that? Those run decks are exceptional because they don't necessarily need to be created by make run deck, but forget that I said that. You should always be doing make run deck. So go in your decks directory, do a make run deck exactly as you had it in the tutorial instructions, and then compare the whatever you created with those. And we will be monitoring the chat window, or even feel free to unmute yourself and ask a question here if you think that it is of interest to the whole group. And we will continue the presentation at exactly 15 minutes. And I will not be stopping the recording in case someone asks something. can change the slide that is being presented with the one that will help you see the instructions on how to make Rendex. And you don't need to worry about the get input data line. So you just need to go into your decks and do the make Rendex command that you see here.
And just one thing about creating new Rendex, I guess that's probably not in the slides. The model actually tries to prevent you from overwriting your own work. So if you try to execute the same command, make Rendex twice, it will tell you that it cannot create new Rendex because it already exists. So you can always specify overwrite equal to yes, and the model will prompt you so that you can overwrite it. But typically, the model just stores all Rendex that you create in some directory specified in your model ERC, and it wouldn't overwrite those by default. So just keep that in mind. That's basically for like done to do safer production work.
Igor, can you check the chat window?
Okay, guys, so how is it going? All good? I'm going to stop sharing the presentation and start sharing my terminal window. So we will see together what you are seeing right now. Do you see my window? Is the font size okay?
Looks good.
Perfect. So move this to the side. Okay, so still okay? Because I had to do some resizing.
Yeah, Andrew says it's overlaid over the slides, although it does look a little funny. I don't know why it's doing that. Maybe did you
Well,
unshare and then reshare? Maybe that will work better.
No, it's doing that. How about now?
Better.
Okay, yeah, my windows are semi-transparent, and I just put some white window under behind it.
Yes.
Okay, so let's see. What we have here is I have created 4 rundex. Can you see my cursor by any chance?
Yes.
Excellent. So I have created the 4 rundex that I was having in the slide, and I added at the end the KT for my initials, which is something that I typically do because it's easier to track when you're setting computing resources. So let's go see differences. So I'm going to show you first the differences between the P4SM40, which is the rundeck with the prescribed sea surface temperature and the sea ice, and the P4SQ-M40, which is the same thing but with a Q-flux ocean. And so starting from the top, the first line shows that you have a different name, and then there are some comments here that are different. You can ignore those. Then we are going into this part here, which says on the left side, the prescribed ocean has the OSST file, which contains the sea surface temperature data, and the S-ice files that contain the sea ice data. And these files are gone from the Q-flux, and they have been replaced by the OHT file, which is the ocean heat transport information to be used in that ocean. And you see in the file name of this OHT file that it says 65 meters. So you know that, at least if the documentation is right, that the file, that this ocean has a 65-meter depth assumption. One thing, since we are here, you know, in Fortran, you need to, when you open a file, you need to say what's the file name. The way we have it in working is that taking for example, this OHT file here, whatever is before the equal sign is what the Fortran code will see as the file name. So if you do an open OHT, then the code will see it. And that makes things easy. You don't have to worry about file names because you just create some short things there. So if you want to read a new file, whatever you put before the equal sign is what you need to use in the code. Then there is this line down here, which is the line I told you with the label and name list. It contains the run ID and then some comments. And it just says that these 2 rundex have different name and a little bit different comments. Then this K-ocean line is not really different. Well, yes, it is. This one is K-ocean equals 0. This one is K-ocean equals 1. So on the left side, the ocean is prescribed, so you don't have to calculate it. On the right side, it is computed. It's not fully dynamic, but still it is computed. So it is equals 1. And then there are 2 lines at the further down, the U not A and the WMU multiplier. These have to do with the cloud balancing, which is different for every different physics configuration. And so these two options are different physics configurations, and that's why these things are different. Other than that, that's it. The Randex, the key difference that the Randex have are the sea surface temperature data file, the sea ice file replaced by the OHT, the ocean heat transport, and the K-ocean, nothing else. So it's very easy to switch from one to the other. Now let's go see the other one, which is the dynamic ocean against the Q-flux. So the Q-flux, I kept it on the right as before, and the dynamic ocean is now on the left. So at the top, you see again, there is the comments block that is that differs. Of course, these are different Randex, so you need to document them appropriately. Then on the left, there is this line that says define check ocean. And there are a number of preprocessor options here. And I have not discussed about them yet. These define big blocks of code being enabled or disabled, usually big. It can be very small, but it's usually big blocks of code. And so you will see inside the code several places that say, if def something, do something, otherwise else, do something else. And these are defined in here. So it says here that for the dynamic ocean, you need to enable a lot of new stuff. And that's why we have it protected under the check ocean directive. Then there are some files that are different. So the ORES is the ocean resolution file. This is irrelevant for the Q-flux. It does not have a resolution really, it only has some depth. And then this one, so we have to define a source file. This is a Fortran file, right? It can be a .f or a .f90 file. So it contains all the information from that. Then further down, you see the QUS3D with the TQUS DRV. The two different Randex use some different advection codes for some historical reasons. This is gone now in Planet 2. They use the same, so you don't have to worry about that. It's not a core difference between the ocean flavors. And then there is a big block. There is a big block of. Sorry about that. There you go. So there is a big block of blue lines here on the left, which are these are the source files, Fortran files with all the code that is needed to execute whatever happens inside the ocean. And there are plenty of files there. And then there are some differences that they are not relevant, like the first 3 lines that you see with the AICs there. These are all commented out with that's why they start with exclamation marks, so that you don't have to worry about those. And then looking down here, there are some differences now. The ocean has the OIC file, which has already been mentioned in the chat window, interestingly. It is the ocean initial conditions. And you see that both versions of both Randex have an AIC, atmospheric initial conditions, and GIC, ground initial conditions, because they both have an atmosphere and ground. Now the flavor on the left now has an ocean, and it needs to have some initial conditions to start from. And then there is the topo file is something that is practically the same between the two module versions. It is just in a different location. That's why it shows up differently. But there is the topo OC, which contains the bathymetry of the ocean. It's like the topography underwater. And then there is the O straits, which is the ocean straits. Occasionally, certain passages are too narrow to be resolved by the model resolution. So we have to prescribe and say that, you know what, there is the possibility of having water flowing from here to there, although in the model resolution you don't see it because it's too coarse. So this is how this is where in the code you define those things. Then there are certain things further down that are just differences, you know, in the Randex themselves, that they are not exactly consistent, but they are just the same things in different locations, so you don't have to worry about that. And then again, you see down here the different name. K-ocean now is the same. and then the tuning things, and that's it. So essentially, although the dynamic ocean file configuration is very different, much more sophisticated than the QFlux, it only has 3 major components that are different. One is that you define at the beginning that the ocean is dynamic, the check ocean line. The other is that you say, here are the Fortran files to use. And the other is that you say, here are the input files to use. And everything else is the same. So you see now the value of having Randex as the single go-to place for configuring your world. It's if you consider, for example, the difference between the prescribed ocean and the QFlux ocean, essentially the difference was a couple of input files and the K ocean line. There is no need to have a different Fortran file for such trivial changes. So we do everything in here, and then we sync them in the code. I think we will mention at some point later how to do that. And then just for fun, I can show you how the dynamic ocean compares with the Mars Randex. And again, there are some comments at the top. And then if you see further down, I'm not going to discuss a lot of things. The dynamic ocean on the left has plenty of, again, all the dynamic ocean code, the Fortran files, that they don't exist on the land, on the Mars side. And then further down, you see there are so many differences, it's just impossible to enumerate. Just because you see, it's essentially the whole thing is different. Just because having a very simple planet like Mars does not require a lot of weird stuff to enable, and then the configuration of that planet is fairly straightforward. It's not easy. You need to create the input files, you need to test things. It takes work, real work. Never underestimate the amount of work that is needed for creating a new planet. And this is why we have Chris with us to explain that tomorrow, because it's not simple. And but creating a land planet is simpler than creating a planet that has both ocean and land. I'm going to share now the slides again. So we stopped here. And then this is the last part of every Randex here that you see in the input Z that I mentioned earlier. It explains the time, the internal time of the model. So it can be nominal years. It can be just it can be real years. So if we're discussing about the present day Earth, chances are that when you say 1850, you mean probably the actual year 1850. What am I doing here? So but for a planetary simulation, the years don't really matter. So you can use them as indices. So what we do is that we start maybe from the year 1. So 0001. It needs to be a 4-digit thing. There is a way to have it a 6-digit in case you want to do an extremely long simulation. You just need to enable a couple of things in the Randex, but the standard is 4-digit years. So in this example, so there are 3 lines, and they are really important to understand them. I am using this model for over a decade, and I am still making mistakes in those 3 lines. So please check them out, and never trust yourself, because you will be doing the same mistakes here all the time. So year I, this line is when you say that the model will start. So in this example, it starts at the year 1897, the first month, the first date, time 0. And so it starts at midnight, just at the beginning of the first day of the year 1897. The year E line says to the model when to stop. And it says here, stop at the year 1910, month 1, date 1, year 0, hour 0. So the moment it crosses the end of December 1909 and goes into 1910, it immediately stops. And that's important. If you say to the model to stop at the end of December, it will not cross the line from December to January, and it will not save output of that December. You really need to go into the next year, hour 0, to save the last month of your simulation. And then there is the iStart line, which is, if you remember from the instructions you had, there was we said things like the setup hour and then the actual running of the simulation. So the way the model works is that when you start a simulation, you start it from certain conditions that are described in input files. And those input conditions can differ. The most standard thing is what we call a cold restart, which means that the iStart value needs to be equal to 2. And then you use the files that I mentioned earlier, AIC, GIC, OIC, for atmosphere, ground, and ocean initial conditions. I'm not going to cover other options here, but you need to remember that whatever value you pick for iStart, and there will be only 3 values that you can be using, it matters for the input files you are using to start your model from. So for our case, cold restart, iStart equals 2, and those 3 files, AIC, GIC, and OIC, are being used. And then you tell to the model, now start the simulation from those files, and very quickly stop the simulation and save the standard restart file that you will be saving regularly as the run progresses. And we say here that the year E for this initial very short period will be 1897, month 1, date 1, hour 1. So if you compare with the first line, the year I, it is 1 hour later. So we tell the model, run 1 simulation hour. That's why we call it the setup hour. Stop and save the restart file that you will be saving either way. And if you look at in your run deck at the very bottom, there is a line that is saying end disk. This line tells the model how frequently to save the restart file, just in case, because you might want to run a 1,000-year simulation. You do not want to risk that something will go wrong and you don't have checkpoints in between. So you tell the model, you know what, every number of time steps, and that number of time steps is defined by the end disk variable, save a checkpoint file. And if something goes wrong, you will be restarting from that one. If nothing goes wrong, then just keep overwriting as the simulation goes. And as a matter of fact, there are 2 restart files. It saves alternatingly, it alternates from one to the other. So if something goes wrong at the moment that it is saving a restart file, then you have the previous one. So nothing can go wrong really, except very few cases. And so essentially the iStart equals 2 line does exactly that. It tells the model start and immediately save the checkpoint file and stop. And then you submit your regular simulation as pretending you are restarting the simulation, and you put it into your computer's queue if you have a supercomputer, for example, or you just put it on the background the way it's described. So this, do you have any questions on that? Because it's really important to understand this. It's very common that you make mistakes here. I'm not monitoring the chat window, but Mike and Igor are, hopefully. But if anyone has anything to say, you can ask now about this.
Yeah, we're looking at the chat window. We answered, Chris and I have mentioned some comments about if you have a very long set of runs.
Okay, perfect.
That You might have to use 5 digits. For example, Proxima Centauri has an 11.2-day period.
Yeah.
If you look at our template run deck for that, it goes over 10,000 orbits, and we had to put in longer numbers.
Yeah, I think that
you can't extend. Yeah.
I think it's up to 6 digits, the maximum that we can do.
I think that's correct.
Okay. So I don't hear anybody speaking, so I will continue. One extra thing to say here is the line I have at the bottom, master year equals 1850. So master year comes from the Earth side of the model, which means that, and it exists to be able to run either transient or climatological simulations. When you set master year to a certain number, you tell the model, I want you to use the greenhouse gas concentrations and any emissions that are prescribed for that year, no matter what the year I and year E tells me. So if master year is a number other than 0, then year I and year E lose their meaning as literal values, and they are just indices that they count the number of years that you have simulated. If master year is 0, then you run the model in transient mode. So if you have interannually varying emissions, the model will be using those depending on what the year I and year E says. Essentially, what the years actually mean those years. And the greenhouse gas concentrations can change with time. Again, the actual year defined from where you are between year I and year E will do those things. For planetary simulations, I don't think that anybody ever has used transient simulation. So we always use a master year value of whatever. We use 1850 just because, but you can use any other value you want, as long as you remember that when you will be defining your greenhouse gas concentrations, and we'll get to that, you remember that you need to say that the year is whatever master year says. You'll see what that means very soon. We've done that. I will stop the technical part to say a little. I have a couple of slides on science, and then I will, and then Tony will take over to discuss about the ocean. So the running with tracers, as I mentioned earlier, is big. It adds a lot computationally into the model and creates much more output as well. So and then it also has plenty of requirements. So if you want to say, I'm going to simulate the methane cycle on Mars because it's cool and I want to see what happens with methane up there. That's fine. You can use a chemistry if you believe that this chemistry we have is valid for Mars. But you don't need to only enable chemistry. You need to create input files that create certain things about sources. You need to handle the sinks if there is something Mars specific that does not exist on Earth. So it has work for that. Sunny is working with the KPP, which is the kinetic preprocessor that will enable us to change chemistry flavors much more easy compared to what we have right now, which is plenty of hard coding in there. But this is not ready yet, and at some point it will be. Then for aerosols, I mentioned that we have Omine matrix. The slide also shows Thomas, which is a version that we have in Planet 1.0, and it's going to be abandoned very soon because we don't have the manpower to hold 3 different aerosol schemes. So we stick with the first 2. So OMA has only one moment aerosols. As I mentioned earlier, it resolves the size, does not resolve the size, but it resolves the amount. So if you have 3 different aerosol types, you know at any given point in time in every grid box the actual concentration of those things, but you don't know the size of them. You just use the prescribed size that you have. Matrix resolves the size distribution, as you can see there. There are different modes that you can see with the colored lines, And then when you add them together, you get the black line on top, which is a net size distribution of the result aerosols. And I'm not going to discuss about the Thomas thing. It is extremely expensive computationally, and this is one of the reasons why we abandon it. Now, in terms of new planets now, frequently, almost always actually, people care about the greenhouse gas concentrations of those planets, whether they have clouds, whether they have hazes, and things happen in a uniform way, or maybe with different profiles of hazes, for example, but they don't resolve things prognostically. Occasionally as well, there have been studies that are using Earth fields to drive certain other planets just because there is nothing better to do. And this can be problematic occasionally, and there are easy ways that you can work with these. So methane is, depending on in which planet you are simulating, might have a very long lifetime, so it can be considered well mixed, but it might not. Like even on Earth, it has a 10-year lifetime, so there is a hemispheric gradient that matters. So if you want to resolve something more sophisticated in terms of this greenhouse gas, you might want to enable chemistry with all the caveats I mentioned about computational and work. Then ozone is something that you also need to consider. There is the option to run with some prescribed ozone values, but you need to know what these values are. And depending on your planet, you might not want to use a present day Earth ozone field, for example, because it will generate your stratosphere, and maybe that planet might not have a stratosphere. So you have to keep that in mind. And then for dust and sea salt, even for planets with no vegetation and no humans, if there is land, there will likely be some erosion, so there will be some dust grains that can be lifted by the wind. So it is straightforward, very straightforward actually, to enable dust in your simulation. It is less straightforward to simulate that properly because dust is a wild card even for present day Earth. There are things related with the size distribution of it because it goes from fine to coarse. It is extremely hard to simulate the exact sources in the large grids that global models have. So to compensate for the subgrid scale that you are not resolving, there are some tuning factors that every single model has for dust. And we also have that. And it's easy to tune your dust on Earth because you know how much there is. It's straightforward to tune your dust on Mars because you also know how much there is. We have data from there, but for any other planet that you can imagine, you have no measurements. So if you want to simulate, let's say Proxima Centauri, and you say for a minute that there is some land there, and then you say that you want to simulate dust, there is no constraint in simulating the subgrid scale variability that this planet would have. So you have to rely on what Earth has and say, you know what, this is what I'm going to be using. So big caveats, but you need to decide whether you prefer to not have dust at all or to have a prescribed level of dust based on who knows what, or you have a dust that is prognostic, but you don't know how to constrain it. So very hard answers, very hard questions to answer. For sea salt, it's less complicated because we have a little bit of better understanding of the sources depending on the size. But the key caveat here is that in order to simulate sea salt from a saline ocean, you need to know the salinity of it. And for any other planet other than Earth, we do not know the salinity of their oceans. And that will be a free parameter. And then, of course, there are other aerosols. One can envision that there is vegetation in some other planet that we're seeing, and there might be fires, who knows, if there is oxygen on that planet, of course. So there are other things, like one very important type of aerosol that one might think of is sulfate that is coming from volcanic activity. It can even be ash that is coming from volcanic activity. There are a lot of things, but all these aerosols are affecting clouds. So an important, the easy decision that almost everybody is doing right now is that they are even saying, we assume there are none of those guys, or we assume that there are some prescribed levels, and work with this. And these affect your cloud distributions, and you just need to be aware of those things. Yeah, these are things that we can do with ROCKE-3D. We do not have standard configurations, meaning template rundex for that. But if you care about those things, you should contact me, and we can take it from there. So I don't think I have another slide. Oh yes, I have this last one. So there are 4 more things that I need to mention before finishing the technical part. There is a file that is called I, uppercase I, and that is inside your model output. This is a rewriting of the run deck, but stripped with things that don't matter at runtime, like which files have been compiled. That is irrelevant when you run it because you have your executable. And but or the comments you have in the run deck. These are just comments, they don't affect your results. But there are all the other things are there, like the start and end times, the input files, and the parameters. And there are some really nice ways you can hack your model while it's running to make certain things happen. It can mess up things easily if you're not careful. So depending on how your projects work, you might start modifying this file. You might not. It is something that you need to remember that you need to have there. So essentially what happens is that the moment you do the make setup and you run your setup hour, the run deck becomes irrelevant. It will never be used again unless you do make setup again. The I file is what is being used by the model. So essentially, as the model is running, you can modify your run deck, and that will have no effect on the results, but it might confuse you in the future when you will not remember what exactly you have done. Then there is the log file. It's a file that
Wait, could I mention something quickly, Kostas?
Yes.
But I just want to mention quickly. So for example, let's say you run your model for 1,000 years. You do some analysis, you realize it's not in radiative equilibrium. You just want to continue the model running. You go into the I file, you change year E to the number of additional years you want to run, and then you just restart the model. You don't have to recompile it, nothing. You just restart the model after you've changed just the I file, and then you can move on.
Yes.
Just as a comment. So
I think that this is the most common way to use the I file.
Yeah.
So then there is the log file. It's literally called log, and it lives in the same directory where your output is, same with the I file. And it is an empty file, if I remember correct. It is just being generated by the model the moment it starts running. And it stays there until the moment the model ends gracefully. So if it crashes, the log file will survive. If the model is still running, the file will survive. And that is as a safety net to tell you that this model is running or there is an issue with it, and you will not be able to start a simulation with the same name by accident, and then start overwriting the run that is already running, and then have nasty things happening. Then there's this thing that we call compile with traps, which is for debugging. You enable it with the long line that you see here. You just say make setup blah blah blah. You put all the options you have there, and then at the very end you put that. The case matters, and in the F flags you see minus uppercase O 0. So you enable that. It is very important to do make clean before compiling and running the model with traps, and after, so that you will not be running with traps your standard simulations. This is only for debugging. So if there is a problem that you cannot figure out, or it tells you a segmentation fault, which is maybe because you divide something by 0, the model will not tell you because it is not checking to save time. So what you do is that you do a make clean, compile with traps the model, you run it until it crashes, and then you will get a comprehensive message, most likely. You fix the problem, you do make clean again, and then you compile again without traps to do the simulation properly. And then there is this other feature that is called SSWE. And if you want to call it from the dex directory, this is how you call it, /exec SSWE and then the run ID. And that will stop the model gracefully. So there can be a number of reasons why you want to stop the model. In our case is that we have a 12-hour limit in the supercomputer for running the model, or 24 under certain conditions. So the model, one single simulation hardly ever has enough time in 12 hours to finish. So we need every 12 hours to stop the model, not kill it, just say, hey, 12 hours are gone, stop it, stop here, save a checkpoint file, and then resubmit. Other scenarios might be that you want to shut down the computer for whatever maintenance reason, or maybe you have occupied all the CPUs and someone has something really urgent and they ask you politely to stop your run for a couple of days until they are done and then you can continue. But in any case, you do this and you tell the model stop gracefully. And remember that the model cannot stop gracefully instantaneously. What this command does, it just goes into a file that the model is checking every time step. And it says to the model, next time you can, please stop. And then when the model reaches the time that it checks that file, it will say, hey, they told me to stop. So it will save the setup file, the checkpoint file, which is the restart file for next time, and then it will stop. So it might take, depending on how expensive your model is and how fast your computer is, it might take anything between a few seconds to up to a minute or two. So the moment you run this, just be patient, the moment model will stop. And I am now certain I am done. Any questions before we move to Tony?
Yeah,
I should mention one. Go ahead, Igor, you go first.
Yeah, I just wanted to mention about ifile. Yes, you can modify it, but basically you should consider that it's a hack. So yeah, the best way to use it just to modify ending date. If you for some reason want to modify a lot of things in your run when it's running, it's better just to modify your run deck and then do make setup. Make setup is not supposed to overwrite your checkpoint file or any existing output, like any existing diagnostics. So you can relatively safely make setup again and then just continue run. Just make sure that you don't do cold restart. You just do warm restart to continue from checkpoint. So that's one thing. Especially if you, for example, if you want to change input files, it's difficult to change them in a hackish way. So it's much better just to change the run deck and do make setup again. Then all symbolic links will be properly updated. And the thing about compiling with traps, just wanted to explain that you don't do this for production runs because the model becomes runs several times slower, maybe like 10 times slower with traps. So it's useful for debugging, but you don't want to try to run model for a long time with traps because it's just too slow. Yeah. And maybe let's think about stopping model with SSWE. Yes, that's the way to stop the model. But also, if you run your model on your laptop and you just try to stop it with Control-C or with signal 15, you should be aware that signal 15 is intercepted by the model and it behaves the same way as if you executed SSWE command. So it may not stop immediately, it will try to stop gracefully. So if you stop the model with Control-C on your laptop, please wait maybe a few seconds until model finishes the time step, and then it should quit. Yeah, I guess that's what I want to say.
Yeah, that SSWE command should remove the lock file as well. That's one thing it does.
Yeah.
And also, if your model is crashed, but it still appears to be running, which happens sometimes, this SSWE may not stop the model. You might have to kill the process directly with a kill -9, just so you're aware. I run into that problem frequently.
Yeah,
So.
same with me. Any
Well,
questions?
Yeah, that usually happens on big computers. It's not like the model is running. The model basically has crashed already, but the computer still thinks that it's running, so all nodes are occupied. But basically, yes, executing SSWE will not produce anything because actually no
Yeah,
like
the
real
model is
process
not
is running.
running.
So,
Yeah.
yeah, so you will not see it on your laptop, I think, but you may see it on a big computer that it looks like the model is running, but actually it has already crashed. So yes, you have to kill your byte shop.
Yeah, that's why it's a good idea that if you are running on a large computer system, to check the status of your runs. So I have a little script I write that tells me when the last output file was generated. And if I notice that the last output file was generated 5 years ago, or 5 days ago rather, or 5 hours ago. Yeah, exactly. I know that, well, when you're busy, I know that the run has died, and I probably should go and look at it, figure out what crashed the run if it isn't already completed.
Yeah, usually model does a lot of output to .prt file. You will see that it grows pretty quickly and it's huge. So if for some reason model stopped putting any output into that file, that should be considered with suspicion. So if there is no output in PRT file, that's probably it could mean that your model has already crashed. But usually the last message in PRT file would be something meaningful, like crashed in such and such program because of such and such things, and then there is no output after that anymore. But on big computer, it will still look as if it is running.
Yeah.
Okay, so I'm going to stop sharing, and Tony, you can take over.
Yeah, Tony Labossiere is going to talk to us about the ocean for a few slides, and then we'll take a lunch break. Tony, you hear us?
Can you hear me?
Yep, we hear you.
Yes.
Let me try to share my screen. Can you see my screen?
Not yet.
Sure.
Or one of us could share the screen and we could just advance it for you.
Maybe Mike or Costas, if you can put back the presentation for.
Yeah, I can put it back, and then you will be telling me.
Sure.
When to move.
Perfect.
So share. Okay.
Excellent.
Perfect. So hello everyone. Let's get deeper in the ocean. No puns intended. So depending on what your research is focusing on, there are 4 different implementations of our ocean model, ranging from standalone atmosphere to standalone ocean runs. Let's start with standalone atmosphere runs. So as Costas showed you before, if you have a file with your sea surface temperature, you can prescribe the SST, and that's the only data that the atmosphere will receive from the ocean. And only the atmosphere component of ROCKE-3D will run. And that's why it's a relatively computationally cheap implementation when compared to a fully coupled run with a dynamic ocean you have to process at each time step. The second point, the QFlux mixed layer slab ocean is a second way of running a planet with an ocean, where we use a slab ocean model coupled with the atmosphere. Our global climate model is now coupled with a thermodynamical ocean instead of a fully dynamic one. And we compute the internal heat content Q of the mixed layer, hence the Q flux, to account for the exchange of heat between the atmosphere and the ocean. And this is also relatively cheap, computationally speaking, when compared with a fully coupled run. Now, if you want to get the most realistic run for rocky planet with both an atmosphere and an ocean, you're going to have to run the fully coupled version of ROCKE-3D with a fully dynamic ocean. And this is, as you can imagine, much more computationally expensive than the first two options, as the dynamic ocean has to calculate at each time step things like the momentum equation for the ocean, the vertical and horizontal mixing, the ocean tides, and there are a lot of physical processes that are calculated. But it gives you a much more physically accurate representation of the whole system. And finally, at the opposite of the standalone atmosphere, we also have the option of running a standalone ocean. If you provide the ocean component of a ROCKE-3D with files containing things like temperature at the surface, salinity, wind speed that the ocean sees at its surface, then you can run in standalone run. And this is a way to also get information on the ocean component when it's isolated from the atmosphere. And it's also for similar horizontal resolution, much cheaper than an atmosphere run. The ocean component is usually less computationally expensive than the atmosphere. Now, Kostas went through the comparison of the run deck. If you compare your run deck P4SQ for the QFlux run and P1SO for the fully coupled atmosphere ocean run, you notice quite a few specific ocean files. For example, I'm not sure if we spoke about this ocean, the file called ORES. That's where you, it's in the model directory. That's where you specify both the horizontal and vertical resolution, as well as a few other parameters related to the mesoscale diffusivity. If you scroll down the files, you also saw that there were a lot of specific ocean-rated files that were present in the fully coupled run deck. And as I explained, these subroutines handle all aspects of the ocean, from the horizontal and vertical mixing to the interpolation and the coupling between the atmosphere and the ocean. Another part of the run deck that was different, you see quite a few new input files. Kostas showed one labeled OIC for your ocean initial condition that include the temperature, which is actually specified as an enthalpy, the salinity, which is specified in a PSU, and the mass layer of your ocean at the beginning of your run. Quick question, can you still hear me?
Yes, we can hear you.
Okay. Another file is your topo underscore OC file. That's where the topography of your ocean is specified. So you are going to specify in this file things like your ocean fraction, which for our model, there are no value between 0 and 1. It can be either land or ocean, but there are no in between value. That's the file where you're also going to specify the vertical depth of your ocean cells. Another input file that Kostas talked about was the one labeled OStraits, where you specify the list of straits. That means 2 ocean cells that are connected through them. By the way, Kostas, if you can switch to the next slide.
So before switching, let me say one more thing about the QFlux ocean.
Yep.
Based on the points that you have here, in Planet 1.0, the QFlux ocean, the heat transport that we are providing in the template Rundex is for Earth-like simulations. And that has changed in Planet 2.0, that we provide a 0 heat transport between grid cells, which is it's more of a standard for exoplanet studies, as you say in the point, in your point here. So just to remind, that's only to make people aware that if you are going to change from Planet 1 to Planet 2, the QFlux assumption has changed, and that matters. And Tony, I think I gave you remote control privileges. So maybe you can change the slide yourself.
Let me try.
Yeah, let me mention one other quick thing there as well. As I said before, we have run these QFlux oceans with no horizontal heat transport prescribed, so set to 0 for Proxima Centauri, for example. So if you look at our Proxima Centauri paper, you can find the Rundex for that in the directory on the website I mentioned before, and you can pull down the boundary condition files that you need to run QFlux equals 0 type oceans. Okay, go ahead, Tony.
Let me try.
Thank you.
Just use the arrows. Just use the arrows. I mean, on your keyboard. You don't even need the mouse.
Let me try.
Or I can do it if you want.
It's only 3 slides.
The connection seems to be a bit slow. So if you maybe just take over the control and go back to the ocean slide.
So you want
that one.
This one, yeah. So just to go back, one of the parameters that we specify in this Rundex is a K-ocean, and that's when you specify when you're actually computing the ocean. And so for a standalone atmosphere run with a specified SST, your K-ocean will be equal to 0. But for the QFlux or the fully coupled model, you're actually computing your ocean. So that's why it's set to 1. And finally, just a quick tip: the variable called J10 in ocean in F represent the least latitude with the ocean. And as Mike said in his introduction, we still need a land point for of Southern Ocean. That's one of the things that will change in the future. But for now, it's set to 4 by default, and at minimum it needs to be set to 1 to be a land point. Because maybe can switch to the next slide.
Tony, just wanted to mention one thing that you had that in the red about like no partial lands, partial cells for land or ocean. So basically, the thing is that ocean doesn't support partial cells. It should be, if there is ocean in the cell, it should be full cell ocean. On the other hand, land actually can support partial cells. And usually you wouldn't see that because it's like it's either land or ocean. But if you run the model,
let it be clear that for the ocean, it's either 0 or 1. It's a binary.
Yeah, but sometimes you can actually run. We do run ocean on fine resolution grid. In that sense, in that way, your ocean will be still like will not have partial cells. It will be all ocean or all land, but land actually will have partial cells because land is running on coarser resolution. So that's one thing that basically you may keep in mind.
Yeah, but you won't see that in Planet 1.0. You only see that in Planet 2.0. We run the higher resolution land and ocean.
Yeah, it's kind of for the future, but since it's mentioned here, right. I just wanted to tell,
Thanks, Kostas. Finally, I just wanted to add a few points to conclude on the ocean component. A quick list of future updates that might be of interest to the ROCKE-3D community. So right now, what we have is a hydrostatic ocean, where in our momentum equation, the gravity perfectly balances the vertical pressure gradient. And as Mike also said, we're currently developing a quasi-hydrostatic version of the ocean model that will allow us to simulate deep ocean on the order of 10 to 100 kilometers deep, like the ocean we can have under the ice of icy moons like Europa around Jupiter and Enceladus around Saturn. And that entails both a full treatment of the Coriolis force in our momentum equation and relaxation of the shallow water equation. We're also going to be implementing a new parameterization for heat plumes rising from in the ocean. Imagine that you have some tidal heating or geothermal sources at the bottom of your ocean. I think it's in planet, not in planet 1, but in planet 2, we can specify now a map of geothermal heating in the form of a net CDF file at the bottom of your ocean. And finally, we haven't spoken yet about the sea ice, but the sea ice is part of the ocean components. But there are a lot of improvements coming to the sea ice, both on the thermodynamical side. Right now, the thermodynamics of the sea ice is handled on the atmosphere grid, but we're going to move the thermodynamics from the atmosphere grid to the ocean grid. So it's fully part of the ocean. And we're also improving the dynamical core of the sea ice. And that's it for the ocean.
Okay, great, Tony. Are there any questions for Tony before we run off for a lunch break? Okay. Okay. Well, thanks again, Tony. That was great, and also Kostas for that long intro. So we'll take a break now for an hour, and then when we come back, Igor will cover a few slides, and then it'll just be time for questions and answers the rest of this afternoon, and we will stay online until 3 p.m. Eastern for that. So this afternoon is very open and free. So spend your lunch break eating your ham sandwich or your vegan sandwich, and think about what kind of questions you have for us that you're interested in understanding from what we covered this morning, and we'll see if we can answer them. We probably can't answer everything, but we'll try our best. Okay, so we'll take a break.
Yeah, and we need
ahead.
this. We want this to be as interactive as possible moving forward. So, because as I said, there is a lot of real estate to cover, and it is better to cover the things that you care about rather than just having a laundry list and bore you to death about it with all the details here. So feel free to ask all the questions you might have. Okay, so we'll rejoin in exactly an hour.
Perfect.
Okay.
Thanks, everyone.